Hello and welcome to my second virtual lab report. Today I analyzed the motion of a crumpled paper ball as it fell straight down from rest. By utilizing the computer software tracker, I charted the motion frame by frame, beginning just as I let go of the ball and ending just before the ball hit the ground. I utilized a ruler in the background of the video to calibrate the software and achieve more accurate measurements of distance traveled. Through performing such an analysis, we were able to once again display Newton's second law at work in our real world. Unlike the previous experiment, however, I created a computer model that accounts for a net force on a ball caused by an uneven balance of multiple forces. Above are some helpful formulas that will be guiding our analysis. Newton's second law, or the momentum principle, given in the form Vf equals Vi plus F net over m times delta t, is the core idea behind our work, and it is a guiding formula in the creation of the computational models that will be used later in the video. The force of gravity is given by the mass of the object, in our case a crumpled piece of paper of mass 0.0045 kilograms, times the acceleration due to gravity on Earth, given by 9.8 meters per second squared, all in the direction of the negative y-axis, displayed above as y hat. We will also be discussing the presence of a drag force, which influences the ball from the moment it is let go. So why is this all so important? Why does it matter that we can observe and model gravitational and drag forces? Newton's second law is omnipresent in the universe, and nothing can avoid it. The mere fact that drag force exists on Earth is a very good thing. For example, in the absence of a drag force, skydivers would never hit terminal velocity, a concept we'll discuss throughout this video, and would accelerate uncontrollably toward the Earth. Once again, here's the video off of which I based my entire analysis. It seems rather simple, but a variety of forces are at work. The primary force acting on the ball in the time it was filmed was the force of gravity, which we defined earlier to be mg in the negative y direction. My first computational model, displayed here, only accounted for this force on the ball. To create such a model, I made various alterations to the starter code provided to us. First, I changed the simulated ball's mass to more accurately reflect the mass of the crumpled piece of paper I used. Next, I changed the ball's initial velocity to be a zero vector, since the ball is beginning from rest. Then came the net force. Since we are only accounting for the weight force on the ball, I assigned this variable to the variable Fnet. Finally, I manipulated the code to repeatedly iterate the position and velocity update formulas of Newton's second law. This is the heart of the code. Remember, the position update formula is the first integral of the velocity update formula. When compared with my observed values, seen in orange, the model, represented in gray, seems quite accurate for about the first 0.3 seconds. Then, however, the predicted ball moves a further distance in a shorter amount of time than the observed ball. This is due to the fact that no drag force was introduced to the model. Thus, nothing was slowing it down. In reality, the drag force is acting on the ball in the opposite direction of the gravitational force. The drag force is proportional to the square of the ball's velocity, and thus it increases as the ball's downward velocity increases. Through repeatedly plugging in values, I was able to find that the proportionality constant b held a value of 0.002. By adding the drag force to the net force, which up until then was just the gravitational force, I can more accurately reflect the ball's interactions with its surroundings. Running this new model yields results that look much more akin to my observational graph. On my combined graph, this new model is represented in blue. Looking at the two velocity versus time graphs created by my computational models, we can notice several key differences. In the first model, the magnitude of the velocity increases linearly with time. This is because the mass and acceleration due to gravity were constant. Conversely, the second computational model introduced the drag force, which is a variable that increases with increasing downward velocity. This explains the curved shape of the second velocity time graph. If the ball were to continue falling for a greater distance than shown in the video, the drag force would equal the gravitational force in magnitude. At this point, the ball would hit what we call terminal velocity and would not accelerate any further. The net force on the ball would be 0 newtons. If I had extended the ball's fall, the second velocity time graph would eventually level out, and the ball would move at a constant velocity. If I were to throw the ball of paper down instead of drop it, the terminal velocity would not change. Terminal velocity represents an equilibrium of forces, and the system is always striving to achieve this equilibrium, where the net force is equal to 0 newtons. Throwing the ball down with a velocity greater than the ball's terminal velocity will cause the drag force to be greater than the gravitational force for a brief instant, and thus the ball will decelerate back to its terminal velocity. This is represented in this new model, where I set the initial velocity to 10 meters per second in the negative y direction. This model is the same as the second model, except with a greater velocity in the negative y direction initially. Notice how the velocity versus time graph increases as opposed to the previous model's graph.